Let's move on to 3b. Now this is even, I reckon this is even more important. Second order ODEs. If you don't have these notes in front of you, don't worry about it. They've been up since Monday. I did make an announcement. Second order ODEs. These are important, for a lot of reasons, modelling, applications, etc. But you are going to get tested twice on these problems. Twice. Once in the class test, I absolutely guarantee that, and in the end session. All right, so today's, the rest of this lecture is all about this so-called homogeneous case. Now, you won't really understand what that means, but the problem we're going to look at is the following. Now, that boxed equation is a differential equation, and the highest derivative is a second order derivative. So you can call that a second order differential equation. Now, the a's, b's, and c's are just known constants, known numbers. So an example of this might be something like, 2y double prime plus 3y prime minus, 6y equals 0. Okay, that's an example of a homogeneous second order differential equation. Now, by homogeneous, we mean just 0 on the right-hand side instead of a function of x. So this is a more general problem. We'll get to that later. But this is what we're going to look at today. So how do we do it? How do we solve these kind of problems? Well, the first observation we make is that just looking at this problem here, what we want all these derivatives to cancel each other out, so we get 0. So try to think of a function whose derivative doesn't change much when you differentiate it. Exponential? Any other ones? Yes, maybe sine and cosine, they sort of switch if you differentiate them a couple of times with plus and minus signs. So these are all good candidates. 0, who said 0? That's awesome, that's very good, yes. That's perfect, I love it. So is 0 a solution to this problem, H? Yeah, it is. It absolutely is. Right, it's known as the trivial solution. So what we're going to do, we're going to use that kind of intuition to build these general solutions. So exponential seems like a good candidate. Sine, maybe. Cosine, 0. Well, we're not that interested in that, though. So let me illustrate how to solve these problems. Now, the method I'm going to illustrate now is the standard method that you can use. This equation has a very special quadratic associated with it, a quadratic equation. Now, the quadratic equation is based on the coefficients of y double prime, y prime, and y. So, in this case, it's going to be lambda squared minus lambda minus 6 equals 0. What we're going to do is solve that boxed quadratic and look at the roots. So we know how to solve quadratics. You can choose a number of techniques: factorisation, completing the square. This is the formula for the roots. Right, so I'm just going to factorise it. Minus 3. Plus 2. So our roots are going to be 3 and minus 2. Now, some of you may be sitting there going, well, so what? Like, hang on, we're doing differential equations. I did quadratic equations like in grade 9. Well, we're going to use these roots to form our solution. Let me show you. The first thing we notice about these roots is that they're both real numbers and they're not equal to each other. We've got 3 and minus 2. Let's do y of x. Now, I've made a pretty big leap there. I'm claiming that the roots to that special quadratic can be plugged into these two exponential functions, and I can form a general solution for any constants, big A and big B. Now you can check that that underlined expression for y of x does solve the original equation D, differential equation. Okay, just differentiate it a few times and plug it in. But where did that come from? Where did that come from? The only intuition we have at the moment is that, well, we want some sort of function that doesn't change too much when you differentiate it. These have both got exponentials in them, so that's kind of on the in line with our reasoning there. But let me actually show you where this comes from. Now I must tell you here that this solution is fine for a class test, anything like this. You wouldn't do it the way that I'm going to show you now, but I actually just want to show you that these things, you know, they come from somewhere. They don't just fall out of the sky, right? So what we're going to do is, if you look at this coefficient of y prime, I'm going to split that y prime up, okay, in the following way. And it's going to relate back to this equation. Now, why did I split that into these two things? Well, also, look at the coefficients of these guys. They're here, -3 and +2. Now, what I can do is rearrange this left-hand side to get the following. I'm just going to bracket it off. So all I've done now is just sort of bracketed this off and taken out a factor of 2. Now, what's the relationship between this bracket and this bracket? Anyone tell me? That's just the derivative. This is the derivative of that. So what I can do is make a substitution and turn this bottom line into a first order problem that we know how to solve. We know how to solve it. So I'm going to let, say, this be u and this be u, same thing. We get du dx plus 2, du dx plus 2u equals 0. We can solve this in the bottom right-hand corner. It's going to be an exponential. And then I can back substitute. Once I know u, I can go back here and solve this for y. Okay, so u is going to be something like c e to the minus 2x. putting it back in here because u equals y prime minus 3y. It's a linear first order problem. Okay, it's linear to obtain the following. So essentially that second solution broke the problem down to stuff that we already knew. We already know, hopefully, or we will know by the end of the session, how to solve linear differential equations, first order, and separable differential equations. So I kind of sneakily factorised it and substituted it in to make a first order problem. Then I solved it, right? Now note that you might be thinking, what happened to this C here? Well, when you solve it, you get something like, I don't know, minus C on 5 or something. And I've just defined A to be a new constant involving C. Anyway, do not worry too much about this method. I'm just showing you why it works, basically, and where it comes from. What you would do in an exam is absolutely concentrate on this method. It's cleaner, it's faster, and all this is not necessary. Okay, it's not necessary. So let's actually look at the problems that you might have to solve. Now, just before we do that, the way I split up that differential equation, the 3 and the minus 2 here are solutions to this quadratic. Now we saw this quadratic in the original solution method. So what we normally do is look at the differential equation, write down the associated quadratic characteristic, and solve that. Okay? So in general, if you have, say, I don't know, a general differential equation here, A and B and C are constants, this is the associated quadratic, the characteristic equation. So the analysis for this problem gets shifted to the roots, finding the roots of this problem. That's all it is. So let's do an example. Now, the solution type, I said exponentials are a good place to start. The solutions depend on what kind of roots have you got. In the previous example, we got, but the roots were real numbers and not equal. Well, there's other choices here. You can have real numbers that are equal. So your roots might be 2 and 2. Or you might have complex roots. These are all possibilities, and your solutions need to be adjusted accordingly. So let me show you how to solve this problem here. Okay, so you can see we've also got some additional information. We've got initial conditions, but there's 2 of them. You need 2 because we've got second order derivatives in our problem. All right, 1's not enough. All right, so our characteristic equation it's going to be lambda squared minus 4 lambda minus 5 equals 0. So what we want to do is, first of all, find the roots of that problem. Oh, yes, thank you, minus 5. Let me adjust that. Thank you. So again, you have a choice now. You can maybe factorise, you can complete the square, use the quadratic formula. This one will factorise. Okay, so it's going to be what? Minus 5 and positive 1. So the roots 5 and minus 1. Now we can see that we need to analyse the roots, right? These are both real numbers and they're not equal. And up here it says when the roots are real and not equal to each other, then this is the general form of your solution. It's just a combination of exponential functions. So let's write that down. Okay, this is the general solution. Now, a good question here is, does it matter which way you put the numbers in? What about if I put in a e to the minus x plus b e to the minus b e to the 5x? Does it matter? Why not? Yeah, it doesn't. Right, it doesn't matter because the big A and big B are just arbitrary. They're just constants, so it doesn't matter, right? So if you have these choices reversed, you'll still be correct. We haven't used the initial conditions yet. Right, so let's go through and determine big A and big B from the initial conditions. So our initial conditions give the following. First of all, y of 0 equals 1. So we go here, we plug in x equals 0, and we're going to get a plus b. So that's one equation. The second initial condition, we differentiate and plug in x equals 0. So that 5 is going to come to the front, that minus 1 is going to come to the front, and we're going to get something like this. So now what you want to do is just solve those two simultaneous equations. All right, so if I just, add one equation to the other and rearrange, I'll get the following for A. And then you can back substitute and get B. So, our final solution then can be written out. So that's a good example of something you might get in a class test, possibly in session. Transfer the analysis from the ODE to the quadratic, the characteristic equation. Solve it, look at the roots. If they're real and equal, then the general solution is just a combination of exponential functions. That's it. Okay? If you want to be a bit technical, you'd say it's a linear combination of exponential functions. You might have heard of that in algebra. Questions? Yes? Sorry, say again? I still can't hear you. A quadratic polynomial? No. Well, for A, B, and C identically equal to 0, yes? Yeah. Yep. So it comes back to what's your name? Alex. Come back to what Alex said. 0 is a solution. So that's good. Any other questions? Yes.
What happens if the roots are even?
Equal? Oh, that is an excellent question. The question is, what happens if the roots are equal? Well, if the roots are equal, then this no longer necessarily applies. Okay, it's a bit of a twist. So we'll have a look at that in a second. There was a question over there. So that's coming up. You're about minutes ahead of me. Oh, okay, yep, good. Okay, so this is only for the case when the roots are real and not equal. Okay, so let's talk about the repeated roots. Now, you can see what I've done up here is just use the same general method that I used in the first exercise or example, breaking it down to the analysis of a first order problem. Okay, you can see I've split that up here and then made a substitution. What happens then is you get down to solving some sort of linear equation, and this solution pops out. Notice it's a little bit different to the previous example. You've got a coefficient of x there. You didn't have that in the previous example. Now, if you consider the characteristic equation associated with that previous example and you solve it, this has got a repeated root, 2 and 2, positive 2 and positive 2, solve that. Right? So that sort of method works in general. If there's a single repeated root, this is the general form. So it's almost like the previous one, except you've got an x in here. Now, a lot of people forget that in the exam. They forget that in the exam. So don't let you forget it. Yes?
Now, is that meant to be lambda squared minus lambda? Is it plus 4 or minus 4?
Let's have a look. Let's have a look. Hang on. We'll just go back to the original equation. Oh yeah, plus 4. Thank you. So it would be, yeah, plus 4, right? Thank you. Right, so the bottom line is, if you solve that characteristic equation, you get real and equal roots. It's an exponential plus x times an exponential, a linear combination of those. So let's do a problem and see how we solve it. All right, so the first step, write down the characteristic. All right, so it's going to be lambda squared plus 6 lambda plus 9 equals 0. So the analysis has changed now. We're not interested in the differential equation anymore. We're just interested in the quadratic, the characteristic equation. So you can solve this a number of ways. You can just factorise it in this case. So here we're going to get minus 3 and minus 3. So as such, we're still using exponentials, but we need a factor of the independent variable, x. Easy. Easy. You just replace a differential equation with quadratic. Easy. Now, a lot of people make the mistake You know, I've seen students, you know, what I try to say is multiply through on this term by x, right? Don't forget the x there. But what I've seen on exams is that, you know, this y might be a function of t here. So they put t here, they put t here, and they put x here. Okay? Don't do it. Don't mix up your variables. It's a perfect solution until you get to the bottom line. You go, oh, so close. Okay, so when I say multiply through by x, I mean multiply through in that second term by the independent variable. Okay? Any questions for that one? That's a standard method. Standard method. All right, there is one more case. When you solve the quadratic and you get complex roots. Okay, they're allowed. Now, from basic algebra, we know that these roots will occur in conjugate pairs. In that case, if you solve the quadratic and you get complex roots, well, the general solution is given by this. We've still got an exponential there, but a linear combo of cosine and sine. So I'm not going to justify that for you, but you can go back and use Euler's formula. It's actually not that difficult, but just remember you need an exponential function, but a linear combo of cosine and sine. Now here, the beta is positive. Okay? The beta is positive. So these betas in here will always be positive. The alpha could be positive or negative, we don't, or zero, we don't know. So let me give you an example of this one. All right, the characteristic equation, let's write it down. So now we're going to try to solve that. You can do it a number of ways. I'm just going to complete the square. Okay, I'm a pretty simple guy. I like simple techniques. So okay, so I'm actually just going to break that 5 up into 4 plus 1. I can take the positive and negative square root of both sides, right? So I'll get 1 plus or minus 2i. Anyway, so what's our alpha and what's our beta? So here, alpha equals 1 and beta equals 2. Our roots are complex. And so our general solution is this. So we just, alpha's 1, so it's e to the x. Beta's 2. Alpha and big A and big B are constants. All right, guys, thanks for putting up with my incompetence. I'll see you all tomorrow.